We have studied shunt, series, and separately excited DC generators so far. Now we'll be studying compound DC generator in this session. We'll be looking at its equivalents and its terminal characteristics. Uh, we already know for a compound DC generator, you have two configurations. One is a cumulatively compound case, and another one is a differentially compound case. In the cumulatively compound case, we understand that the magnetic fields produced by the series field winding and the shunt field winding, they add up, magnetomotive force add up. Whereas in case of a differentially compound DC generator, the magnetomotive force produced by the uh, series and shunt field windings cancel out. So, taking first the case of a cumulatively compound generator, and we'll be taking a long shunt configuration. You have armature resistance, this is RFS, the series field winding. LFS, you have RFP, the parallel field winding, or the shunt field winding, LFP, and terminal voltage. VT. So this is EA minus current IA, the armature current is flowing through this winding. IF is flowing through here, IL is flowing through here. So you have IA is equal to IL plus IF in this case, which implies IL is equal to IA minus IF. And looking at EA versus VT relationship, VT is equal to EA minus IA RA minus IA RFS. So this is your VT equation. We can also find out IF using VT by RFP. So this is case for the long shunt configuration. Similarly, we can find out the in case of a short shunt configuration, what will be the value of armature, what will be the KVL equations, right? Also know that that the number of turns of the series field winding be NS, that the number of turns of the parallel field winding be NP. Therefore, magnetomotive force of the series field winding will be NS into IA. Magnetomotive force of the parallel field winding will be NP into IF. Total magnetic field will be the relative sum of these two magnetic fields. Now going to the terminal characteristics. We have the equation VT is equal to EA minus IA RA plus RS, where RS is the RFS, rather RFS is the series field winding, resistance of the series field winding. And what happens as we increase the load, this VT was I graph. So initially at I equal to 0, we assume VT is equal to EA. So that will be the starting point. Now as we increase the load, IA increases, so we expect that IARA plus RFS to increase and decrease. We expect this type of a curve, right? But it's not so simple. This basically depends upon the number of turns of the series field winding and the parallel field winding. What happens in this case is, whereas IA increases, IARA plus RFS drop increases, that means VT should normally decrease. Fine, but what else is happening in the circuit? We have the magnetomotive force. I'm writing now simply F. I'll write this as Fs and this as Fp. Fs is equal to Ns into Ia. Since Ia is increasing, that means Fs is also increasing, and the total magnetic flux is equal to Fs plus Fp. Since Fs is increasing, that means F total is also increasing. So if the magnetomotive force is increasing, as F total increases, that means flux produced increases. If flux produced increases, that means EA, which is proportional to flux, increases. So if EA is also increasing in this circuit, IRAFS is also increasing, then is VT increasing or decreasing? We need to see that which effect basically predominates here. Whether the EA will predominate, the IARA plus RFS drop, or IARA RFS drop will predominate EA. So this basically depends upon the number of turns of the coil. With a few series turn, case A will be for a few series turns. With few series turns, if there are only few series turns, naturally we assume that the Ns into Ia, the magnetomotive force produced by this series field windings, will be less. It will not be as much, therefore with few series turns where Ns is less, we presume that Fs is equal to NSIA, although Fs will increase, but it will not increase by that much of a magnitude, and EA will not increase by that much of a magnitude. So I am showing it by one arrow here. So EA increases, but it will not increase as much as compared to the drop in IRA plus RFS. Therefore, we'll get a curve like this. So this curve is known as under compound, and in this state the DC compounded generator is known as under compounded DC generator. Second case, where we have moderate number of average number of field turns, larger Ns. With a larger value of Ns, you can have Ns is relatively more Ns. Fs equal to NSIA will increase. I will show it by double arrow. That means EA will increase. The effect of EA will be such that naturally there is also flux saturation, so there is a limit to which flux will increase. After some time it will not increase more. So it's almost flat, right? This effect, and in such a case the motor is known as flat compounded DC generator. Case number C will be for even more NS, Fs will be much larger, EA will be much larger. It will have a lot of it will have a predominant effect over IRFS, and therefore you see a curve like this in this case. Right? So this is your constant value of EA. So you can see flat compounded DC generator has almost a value obtained around EA. In the under compounded machine, you are getting a system. You basically have a system where your terminal voltage is less than the generator voltage. In an over compounded case, your terminal voltage will actually be more than the initially generated uh, voltage EA. So this is known as over compounded motor. Fine. At this point, where this basically this flat compounded motor intersects the EA constant curve, it is basically the full load value current. So we have actually three cases here depending upon the possibility of number of turns of the coil. You can have for a fewer number of turns, you can have for moderately more number of turns, and you can have for a very large number of turns of series field windings. You will be getting different characteristics, terminal voltage characteristics with respect to armature current. Then we have the voltage control strategies of cumulatively compounded generator. Voltage control, terminal voltage control. You have the same two methods. You can control the voltage either by changing the flux or by changing the speed. It will have the same effect as we saw in case of a shunt generator. Fine. And then you have the differentially compound case. Our differentially compound DC generator is different. The total magnetic field here will be Fp minus Fs. Instead of it being Fp plus Fs, we have here Fp minus Fs, where Fp will be equal to Np into If minus Ns into Is. So if we look at the terminal characteristics of this motor, and Vt will be same, the equation will be same, Ea minus Ia Ra plus Rfs. So what happens here, as you increase the load, Ia increases, and in the previous case, in the cumulatively compound case, flux was increasing. But what happens here, as the current increases, Ia increases, hence Ia increases. If this value increases, F total will decrease. That means flux will decrease. That means Ea will decrease. So what you are seeing in this case is both Ea is decreasing. So in this case, it doesn't matter whether Ns is less or Ns is more, because both Ea decreasing and Ia increasing will have the same effect, and that is of decreasing the terminal voltage. Therefore, in this case, what you see characteristics like this. It is the voltage is reduced by with respect to A by a large amount, and as already discussed previously, also differentially compound DC machines rarely find any use. They are not used intentionally, only in certain cases for certain meaningful applications they will be used. They are not used intentionally. Because of some certain operation of the cumulatively compounded DC machine, the differentially compound DC generator is produced. Fine. So this actually completes our DC generators course, and DC machines rather. We'll be starting, I'll be providing you the tutorial sheets in a few days time, and we'll be starting with transformers from the next week.